All right, I think we're we're good to go. Welcome to the lightning talks. Everybody's been told what the order is, so what I'm going to do here is try to, as best I can, keep the time. And so Blessing Andrew Okoro is first. So um, uh, Blessing, you ready to
Hi everyone, can you hear me?
perfect. Thank you. All right, 1 minute starting now. How about that?
Hi everyone, my name is Blessing Okoro. I am a PhD student at SUNY Albany. I'm here to present, okay, I'll be presenting my poster, which we title Sparse Recovery Transmitter Detection Scan. It's a novel approach for accurately detecting and characterizing multiple transmitters in spectrum traces, even in low and challenging SNR conditions. So why does this matter? Because practical spectrum awareness with arbitrary technology is crucial for spectrum sharing. And current methods struggle to detect transmitters and characterize their time frequency activities, particularly when they are dealing with interference and in low SNR and power transmission conditions. So our method leverage sparse dictionary coding to jointly detect and characterize the time frequency behaviors of transmitters when they are of multiple transmitters, which we see in spectrum scans. And yeah, I'll talk about more on this method and our experimental results in my poster. Thank you.
Sure. Thank you. All right. Next we have Kanglei Phil Mu.
All right, so hi everyone, my name is Phil
Perfect.
Mu. I'm from Northwestern University. So our work is entitled Analysis of Spectrum Sharing Strategies for Local Wireless Services. So basically, we consider a scenario where multiple service providers they compete within the proximity of each other. So the question is, how should they coordinate on their spectrum use? So in our work, we consider four different possibilities of possible like spectrum coordination. And some turns out some are preferred by the service provider and some are preferred by the customers. So if you're interested in our poster, please stop by. Thank you.
Perfect. Thank you. And everybody's staying within the 1 minute. So Lee Fan.
You hear me? So our work is a transformer based. We design a transformer based physical layer wireless symbol detection receivers. So we have designed so the pre-trained transformers through context learning has demonstrated acceptable capability to adapt to new tasks using example prompt without any model update. So we design a transformer based wireless receiver. So where the prompt consists of panel data in the form of transmit and receive signals and show high detection accuracy when the panel data are extremely limited, especially only one single panels. And our defined model is like integration of the coherent and non-coherent detections. And our key innovation is that our proposed decision feedback mechanism into in-context learning, where we sequentially incorporate the decision symbols into the prompt to improve the detection performance. And we also define another in-context semi-supervised learning to show that the transformer can extract information from both labeled and unlabeled data during the inference, and have shown the very promising of transformers ability in the advanced wireless applications. And hope to see you guys in the guided talk. That's all.
Perfect. Thank you. All right. Mehmet Sangak.
Hey everyone, so I'm Mehmet Can from Northwest University. Our work is titled Machine Learning Assisted Chirp Detection. We have been forming for radar communication coexistence. As you know, 3.1 to 3.45 gigahertz is being considered for shared use, which is currently occupied by incumbent radar systems, and it requires more agile spectrum management than the CBRS for shared spectrum. So we want to detect the presence of the increment radar at the base station without explicit channel estimation or spectrum sensing, where the radar emits a low duty cycle chirp waveform, and base station does not know the chirp duration duty cycle or has no prior channel state information about it. So what we do is we basically look for anomalies in the residual errors during uplink adaptive estimation of downlink beamformer. And if the radar activity is detected, the communication system immediately vacates the band. And so for that, we basically create a three-dimensional error cubes across subcarriers, OFDM symbols, and users. And we also develop machine learning algorithms, both supervised and unsupervised, to detect the presence of the radar. And that's it. Thank you.
Thank you. Mohammed Oshman.
Hi everyone, my name is Joshua. I'll be presenting instead of Mohammed.
Okay,
So our work is
thank you.
yes, sure. Our work is improving indoor cellular performance. And we know that 80%, so it has been said that 80% of mobile data consumption is done indoor. So the question is now when 5G is deployed, using high power base stations, which suffers from penetration loss and a lot of usage of resources, how can we improve how can we improve indoor coverage? So basically there is a technology called neutral host, which uses a single infrastructure to it uses a single infrastructure to share the internet usage among different operators. So we have taken a lot of measurements from this neutral host system, and we would like to show our findings, which tells us that using neutral host can boost indoor coverage and also free up outdoor resources. So I will be presenting that in the poster session. Thank you.
Perfect. Thank you. Sede,
Yes. Hi all, I am
go
Sedat
ahead.
Tuşa, Okay, thank you. I am Sedat Tuşa, postdoctoral research associate at University of Notre Dame. Today I am going to talk about our evaluation for indoor-outdoor sharing in the unlicensed 6 GHz band. Here at University of Notre Dame Football Stadium, recently about 900 standard power APs deployed, and the buildings adjacent to stadium have already low power indoor deployments. So in order to characterize indoor-outdoor sharing in the unlicensed 6 GHz band, we performed extensive measurement campaign during the game season, during games and after the games. Based on our measurements, we observed that standard power operations outdoors can negatively affect the low power indoor operations. For further details, see you at my poster.
Excellent. Thank you. Shriyanshu?
Yeah. Hi, I'm Shriyanshu, and I'm a master's student at UC Berkeley. My group and I are advised by Professor Nansahai. So our project focuses on how large language models have kind of transformed software development, introducing concepts like vibe coding and copilots. However, a lot of these practices do not perform as well with niche software libraries, which our Spectrum work largely relies on. So we propose a solution called README.LLM, which is LLM-oriented documentation that basically equips LLMs with essential information about a software library. We've tested this README.LLM on a coding task that uses DigitalRF, a library for reading and writing radio frequency data. And across leading LLMs, we saw significant improvements in code completion success rates when README.LLM is included, even when web search was already enabled. So our key takeaway is that as we increasingly rely on LLMs, library developers must make their content easily available and understandable to these models, and README.LM demonstrates a promising approach to do so. Thanks.
Perfect. Thank you. All of these have been great so far. Yadiel Rodriguez Garcia, next.
All right. Hello, everyone. My name is Yadier Rodriguez Garcia. I'm a graduate student from the University of Puerto Rico at Mayagüez under the mentorship of Dr. Rafael Rodriguez Solis. And my poster sort of touches on a novel method of simulating or modeling antenna arrays using an N+1 network representation, where that +1 port represents sort of the incident wave being fed into the antenna array. All of this with the ultimate goal to sort of measure noise performance in receiver systems. So this network model sort of accounts for the antenna coupling between each element and its near and far field interactions. So if you have any questions on that, you can find me in room 1, poster 8. So thank you.
Perfect. Thank. And if you have a poster where you're going to be at let everybody know so we can also catch up with you there. All right, Swaroop.
Hi everyone. I'm Swaroop. I'm a postdoc at Northwestern University, working with professors Randall Berry, Dongning Guo, and Michael Honig. So we are working on how to use beacons for improving spectrum sharing and coexistence. But today my poster is on how to use beacons for CBRS. I will give more background when you come to look at the poster, but in a nutshell, the task of protecting the incumbents in Navy radars in CBRS currently relies on overnight computations of worst-case interference. So this is done in a very static manner. Our idea of applying beacons in the CBRS band is to make it more dynamic, where you are using the real-time sensing measurements from the beacons and real-time control signals, so that we can do this task in a more dynamic manner. And we have some promising initial results on this. And if you come to the poster, you can learn more. Thank you.
Thank you. Tiani.
Yeah. Hi, everyone. My name is Tianyi, and I'm a PhD student from UCLA. My advisor is Professor Daniela Kubrick, and my poster title is Complex Valued YOLO for Wideband Spectrum Awareness. We know that it is an important problem to sense and understand the RF activities in the wideband spectrum, so we can ensure wireless security, enforce RF compliance, and also facilitate dynamic spectrum sharing. To enable such intelligent spectrum awareness, we developed a YOLO-based deep learning framework for simultaneous signal detection and classification by converting the signals into spectrograms. Well, spectrograms are already good candidates for signal detection. We still want to achieve better signal classification results by exploiting the phase information embedded in the signals. So we further developed a complex valued version of the YOLO model, which can better utilize the complex IQ values. We evaluated the model on a real dataset that is captured over the air, and it has already demonstrated better performance in both detection and classification tasks, and also gained better generalization capability across different environments. Thank you.
Perfect. Thank you. Vasu.
Hello, I'm Vasu from the University of Albany. I'll be presenting our lab's work on multispectral transmitter analytics for harmonic characterization. So when transmitters emit RF signals at a specified fundamental frequency, harmonics naturally occur at integer multiples of that frequency. So these harmonics can interfere with incumbent services operating in higher frequency bands, even if the fundamental transmission itself complies with established isolation and power regulations. Such interference has been documented to negatively impact incumbent operations, posing risks to highly sensitive spectrum users, including remote Earth sensing and radio astronomy facilities. So in my poster, I'll be explaining our approach for characterizing faint harmonic activity, which is a first step to addressing these problems.
Awesome. Thank you. Is it you?
Hello, everyone. My name is Zhu Shen from the University of Notre Dame. The research aims to developing methods to identify spectrum sharing opportunities in mostly licensed bands. My study takes the 12.7 gigahertz band as an example. This work is motivated by the growing demand for additional cellular spectrum and potential underutilization of existing licensed bands. We first developed a comprehensive database containing various operational parameters for all incumbent service nationwide. Our methodology consists of two main components. For terrestrial services, we build an interactive map to visualize potential deployment areas across the country and incorporate detailed operational parameters from the database. For non-terrestrial services, we created a flexible 3D terrestrial to satellite interference model, which supports both single deployment and aggregated interference scenarios, and it can adapt to various antenna and propagation models. So welcome to visit my poster in room 2 to explore our findings. Thank you.
Great, thank you. And Zhang Yun.
Hello, everyone. I'm sorry, I just find my camera down, so I have to do sound only. Hello, everyone. I'm Zhong Xie, a PhD student from Northwestern University. I work with Professor Randall Berry. In the poster session, I'll be presenting our work, security investment strategies in shared spectrum markets. We'll look into the situation with the licensed shared spectrum market with a potential attack. We assume the attack can reduce the availability of the bandwidth, and the SPs can invest against this kind of attack. We examine the market outcomes under such attacks and strategic investments. We also try to understand the SP's optimal investment and how the investment cost level, attack uncertainty, and risk aversion impact the market outcome. We find all the possible equilibrium cases under these interactions and find some of them can lead to overinvestment. If you are interested in our work, please feel free to stop by. That's all.
All right, well, thanks. I mean, everyone did a great job introducing their topics, and I think Emily has in the chat link the link to get to the gather to hear more about all these posters. So everybody, great job. The gather link is there, and so I'll turn it back over to Emily or Nick, and thanks everybody. Great work.